Hey, chemistry team, ready for video number 4 on our acid-base series this time. We're going to look at a special class of species that, I'm not going to say they're unique. There's a lot of species that do this, but they can act as both an acid and a base. So they've got an acidic proton, an H+, that is available to be donated to a base, whatever that base is, but they also have the ability to accept an H+ from something, right? Whether they have a nitrogen with a lone pair that H+ can be bonded to, or maybe it has a negative charge. It's an anion of some kind that H+ can come on in. So we want to be able to recognize these, but they can play a special part in things. So we call that amphiprotic. All right, I've heard the term amphoteric before as well, but we're going to go, at least with this textbook, with amphiprotic. So that's any species that can act as both an acid and a base. Pretty cool. It's situational. It's situational. So an amphiprotic species might be like, yeah, I'm just kind of hanging out, doing nothing, and then an acid comes around and goes, woo, you're an acid. I'm going to be a base. And maybe in a different scenario, a base comes along and it goes, ooh, you're a base. I'm going to be an acid. So it can morph itself into whatever acid or base character it wants, depending who it's playing with at the time, right? So let's do a couple examples here. Let's take water, which is your prototypical amphiprotic substance, and we'll take the hydrogen carbonate or bicarbonate ion. Let's look at these both as an acid and as a base. Are you ready? Let's do water first. And we've already seen this. I've mentioned it, but let's formalize it now. So if I'm going to react water as a base, in this case, it's reacting with an acid. You see the acid? That's going to donate its H+ over. Because that's accepting it, this is my base. That will be my acid, right on? So let's look at our conjugate acids and bases. So the water picks up the H+, becoming the hydronium ion, which will be my conjugate acid. And then the acid loses its H+, becoming its conjugate base, which is the chlorate anion. So you got chloric acid going to the chlorate. So base acid, conjugate base. I'm not going to put the conjugate acid bases down because that's not the purpose of this particular video. It's to look at the fact that water can act as a base in this scenario, right? Now let's look at water when it comes in with in this case, I think this is ethylamine, which is a weak base. So here the water is going to donate an H+ over to that nitrogen with a lone pair. So water's acting as an acid this time, and this is my base. So let's take a look at what we get here. So the water loses an H+, becoming the hydroxide anion, right on? And then we'll get the, and that will be my conjugate base, and then I'm going to form my conjugate acid here. I don't think I have enough space, CH3. So many carbons, CH2, NH3 with a positive charge, and there's your conjugate acid. I think that's the ethyl ammonium ion or something like that. So water can be both a base and an acid. That makes it amphiprotic. Yeah! Let's look at something a little less obvious. Let's look at the bicarbonate or hydrogen carbonate ion. Let's look at it as an acid, and we'll do both scenarios ionizing in water. So the bicarbonate ion can ionize in water both as an acid and as a base. Turns out it's going to have a preference, and in the next set for this particular video, I'm going to show you how to predict whether that will prefer to be an acid or a base if it ionizes in water. But first, let's take a look at this reaction. Let's have it acting as an acid. So it's going to donate its H+ over to the water. Right, so this will be my acid. Water will be acting as a base in this case. Ah, that rhymed. You can see the hydrogen there. And the way you recognize that this can be amphiprotic, it's got a hydrogen to give, and it has a negative charge so it can accept as well. Very common. You see anything with a hydrogen in front and a negative charge, that can be an amphiprotic substance. So that's going to lose its H+ to give me the carbonate ion. The water picks up a hydrogen to become the hydronium ion. So the acid becomes the conjugate base, the base becomes the conjugate acid, off you go. And you could look at the acid-base table like we did in the last video to see whether this is product or reactant favor by comparing the strengths of the acid to the conjugate acid and the base to the conjugate base. Now let's look down here. As a base, it can take an H plus from the water. So now this is functioning as a base. This will be, water would be functioning as an acid in this particular scenario. So the base becomes the conjugate acid. That would become carbonic acid, H2CO3, which is kind of special if you look on an acid-base table a lot. It's an unstable acid. It breaks up into CO2 gas and water. Oh, that gets a little weird. And then the water loses an H plus to become the hydroxide ion. So the base becomes the conjugate acid, the acid becomes the conjugate base. But it can function as both. Welcome to amphiprotic species. So let's look next at how you can tell whether it's going to be preferred as an acid or as a base. But we're going to run into a problem there because we're just going to compare the Ka to Kb values. And we'll be able to find one on the acid-base tables, but not the other one. That creates a problem, so I'm going to have to show you a little equation on how to fix that. Be right back. All right, you guys ready to tell whether something's going to be preferred as an acid or base in water? How do we know? Let's take some typical amphiprotic species, the dihydrogen phosphate ion. We're going to look at it acting as an acid in water and as a base in water. So pause the video, predict what those products are going to be, all right? And then do me a favor and write the equilibrium expression for those and see if you can look up on acid ionization constant tables the Ka value for this one. And on the base ionization table, the equilibrium constants, the Kb's, find the Kb. See if you can do that real quick, all right? So pause it, write down what you get and see if your notes match what I'm about to write on the board. All right, here we go. So my acid is losing a base, so that's going to become the conjugate base. I lose an H plus, so I'm going to get HPO4. Since I'm losing a positive charge, it goes from a -1 to a -2. So the dihydrogen phosphate ion becomes the hydrogen phosphate ion. The water picks up a hydrogen, forming the hydronium ion. Right? So Svante Arrhenius would recognize that, Bronsted-Lowry, all those models overlap. So here's my conjugate base, conjugate acid. Let's do the same thing for it functioning as a base. So as a base, it's going to take an H plus or accept an H plus from water. So I'm going to pick up an H plus. So I'm going to get 3 hydrogens now, all attached to the oxygen atoms, plenty of oxygen atoms there. And I'm picking up the positive, which will cancel out the negative. So this will end up being a neutral species, which is phosphoric acid. The water loses an H plus, so I'm going to get OH minus. Svante Arrhenius would recognize that, right? As an Arrhenius base, you see it forming OH minus, Bronsted-Lowry, right? Acid's a proton donor, base proton acceptor. So base becomes the conjugate acid becomes the conjugate base. Now let's set up our Ka and Kb values. So Ka and Kb. So hopefully as you're snuggling on your couch right there, you paused your Netflix binge, right, and did this. Hopefully you're not on Netflix while you're doing this. Hopefully you're on Pandora or your favorite music list or something like that, or just nice and quiet, snuggling with your favorite pet or your significant other. Although studying with your significant other, I found I couldn't focus too much, so I recommend studying on your own. All right, here we go. So I'm going to take my products. I'm going to take my hydrogen phosphate ion raised to the power of 1 times the hydronium raised to the power of 1 over the dihydrogen phosphate ion raised to the power of 1. And I'm not going to include the water because that's a liquid, condensed phase, assume it's constant. For my Kb, I'm going to get the conjugate acid here, phosphoric acid, times the conjugate base, hydroxide, all raised to the power of 1, because we love acid-base chemistry. It's always a stoichiometric coefficient of 1 here, over the original dihydrogen phosphate. Don't include the water. So what we want to do is get our Ka and Kb tables and look these up. So let me go grab my tables. I'll put them up on the screen and see if we can find these babies. All right, I found my Ka table. Wherever you find that, just look in your, if you're in a class, just look in your textbook in the appendix. Now, where you find it, that's part of phosphoric acid. H3PO4 is a polyprotic acid. We haven't done polyprotic acids yet. So it's got 3 hydrogens to give. So this is after phosphoric acid gave a hydrogen. So look under phosphoric acid, right? So if you see phosphoric acid right there, see the H3PO4? And then after it gives a hydrogen, after it gives a second hydrogen, right? You can see as it moves down, the Ka values change. And we'll look at what that means later. But for phosphoric acid, it would be 7.1 times 10 to the minus 3. But for dihydrogen phosphate, it's 6.3 times 10 to the minus 6. Do you see that? So that Ka value is going to be 6.3 times, oh, that's a minus 8. My old man eyeballs couldn't see it. So 6.3 times 10 to the minus 8. 6.3 times, where'd my black pen go? Here it is. 6.3 times 10 to the minus 8. That's a pretty small Ka value, so that's reactant favored, right? Yeah, once I went past 50, I had a hard time seeing things. H2PO4, yep, 6.3 times 10 minus 8. I don't have my glasses with me. Oh, let's take those babies on. Now let's look for Kb. So let's look for H2PO4 minus on our Kb table. So we find our Kb table, and we go, where is it? Where is it? And, oh no! On the test. This is your oh crud moment. You go, I can't find it, and your hand goes up. Professor, Professor, I can't find it on the table. And I go, oh, it's not supposed to be on there. Do you remember how we found it? Now, I haven't taught you that yet, but that's what I'd whisper to you on the test. You'd be like, crap, I should have went to lecture that day. Or now, I should have watched that video, because lectures are so much more cool now because you're at home just kind of kicking back, watching it and clicking and replaying it, replaying it, replaying it. There is no Kb value table. It's not on the Kb table. Oh no, what do we do? All right, call the wambulance. Let me show you a real quick trick on the next board, how to calculate. If you don't find it on the table, we'll be able to calculate it with a really cool trick by relating it to the Ka. We do know the Ka value of its conjugate acid, right? So we can use that Ka value of the conjugate acid that is on the table and calculate the Kb value. Let's do that. All right, you ready for this? This can be a little weird the first time you do it. So we're trying to determine a Ka or Kb value. We don't find it on our Ka or Kb tables. So for the case of the dihydrogen phosphate ion, we found the Ka value, but not the Kb value. You see that pretty common for amphiprotic species. You'll find one, but not the other. Because they don't need both, because you can always calculate the other using this cool little equation. Now, I'm not going to derive that. I could. You can read the textbook and see how that's derived, and not critical at this point. But just know that if you take, for example, if we're looking for the Kb value for this, the Kb value times the Ka value of its conjugate acid will equal Kw. Now remember, Kw, and you'll see varying sig figs here, 1.00 times 10 to the minus 14th. Sometimes you'll see it as 1.0 times 10 to the minus 14th. Just use whatever's provided for you, in your textbook or in exams or quizzes or something like that if you're tracking significant digits. Usually not a big issue. Usually 2 significant digits is totally fine, because very rarely do you see more than 2 on the Ka-Kb tables. A lot of times just 1. All right, but just remember, if you're trying to find the Kb value, you need to know the Ka of its conjugate acid. If you're looking for a Ka value, it would be the Kb of its conjugate base. So since we're trying to find the Kb value here, we're going to look up the Ka value of its conjugate acid. So let's rearrange this, and let's do it for the dihydrogen phosphate ions. So Kb for the dihydrogen phosphate ion. So let's set up this equation. So let's rearrange this. Kb will be equal to Kw over Ka. Simple algebra. But the key is what Ka. Kw is just a constant. Kb we're solving for what Ka. This is of the conjugate. That is the key. It's the conjugate acid right here. Boom. Having fun with our messy board, right? So if I want to find the Kb value of this, because it's not on the table, I take Kw divided by the Ka value of its conjugate acid. And if this was as an acid, we'd look up the Kb value of its conjugate base. So let's look up, now we already know Kw, so let's plug that in. 1.00 times 10 to the minus 14th. And again, we could probably use 1.0 and we're still safe. Let's look up the Ka value for H3PO4. Right? Let's put that in parentheses here. That's where I find most students have issues. They use the wrong Ka value. Right? They actually use the Ka value for this, and you don't. You want the Ka value for that. So let's look up on our acid ionization constant table. Let's look under P for phosphoric acid. Where is it? Where is it? There's phosphoric acid, 7.1 times 10 to the minus 3, if my old eyeballs can see that right. 7.1 times 10 to the minus 3. So you see the two sig figs in there? So we're totally fine doing a 1.0. So sometimes you'll see me use 1.0 times 10 to the minus 14th for the Kw, which is the autoionization of water, which we introduced in a video a long time ago on the introduction to types of equilibria. We did Kas, Kbs, Kws, Ksps, things like that. So that's just water reacting with itself, forming hydroxide and hydronium ions. So we're going to end up with two sig figs in this one. So if we punch this together, I get 1.408. Good to two sig figs. Times 10 to the minus 12. Right? That's pretty weak. That's a very, very low Kb value. And so that does not round up. So that stays as 1.4 times 10 to the minus 12 is the Kb value. So now we can answer our question. Now we have Ka for H2PO4 minus, the dihydrogen phosphate ion, and we have Kb. So what we're going to do on the next board is compare the Ka to the Kb, and the bigger one wins. So if Ka is bigger, that particular amphiprotic species would be more of an acid in water. If Kb is bigger, it would act more like a base in water. So let's put up our Ka and Kb values and determine if the dihydrogen phosphate ion is more of an acid or a base in water. All right, this is going to be the end of our video here. I summarized our results. We're looking at the amphiprotic species H2PO4 minus, or the dihydrogen phosphate ion. We looked at the different reactions of it ionizing in water in both scenarios. We saw that acting as a weak acid, it had a Ka value of 6.3 times 10 to the minus 8. We found that on the Ka table. We'll always find one, but not the other. As a base, we use the equation Kw is Ka equals Ka times Kb. So the Kb in this situation was Kw divided by Ka of the conjugate acid of H2PO4 minus, which was H3PO4. And we got a value of 1.408, good to two significant digits, times 10 to the minus 12. So our answer to our question, does this prefer to be an acid or base, which is bigger? All right. So H2PO4 minus acts as an acid in water because Ka is bigger than Kb, right? Ka is bigger than Kb. The 10 to the minus 8th by a huge order of magnitude, right? We're talking 1,000 to 10,000 times bigger. So it's definitely going to function more as an acid than a base. And we proved it. It could be both. But in water, it's going to function as an acid. And there you go. That's how we deal with amphiprotic species. So we're going to get into some juicy stuff in the next two videos. Take a little break. Take a walk around the block. Try to get some sunshine in there and come back. Refresh your mind. And let's have some fun learning.